All right, warm up. Factoring. Factoring. We should be pros at this by now. What do I need to do? Can that y be right there? Should we change that y to something? To 0. Yeah, we should change that y to a 0. If you didn't do that, not a huge deal. Okay, because you probably did it later in the problem. But either way, it's good to do it now. Get in the habit. Now what?
0. You said 0.
Oh, 0.
What?
I don't know.
What are you saying? No. What is the first step of factoring, guys? Greatest common factor. Okay, it looks like some of you guys did rational root theorem. That's fine, okay? But your constant is 0, right? So you're still going to end up getting your first factor of 0, probably. I think that's the only one you're going to get out. When you take out that GCF, you end up with x squared minus 6x plus 9. Perfect. This was the easiest way to do this, okay? X. Can we go ahead and just set that equal to 0 now? Get it out of the way? Yeah, that's my first answer. Okay? If you dropped it down and continued to the end, that's fine, just as long as you make sure that was one of your answers. Okay? And what would we do now with this? Yep, X method. What goes on top? 9, what goes on bottom? And my 2 sides. Okay, you did it a longer way?
It's the same thing.
It's the same thing. Yep, you can do rational root theorem to solve this. It's fine. We end up with x squared minus 3x plus 9. Then we do grouping. What has to be in the middle? And the first two both have a
X.
And what's left?
An X squared.
X minus 3, good. And the next two?
-3.
And what's left? X minus 3. Perfect. Okay. Now what? And we set them both equal to 0, right? So what are my 2 answers here? X equals 3 and X equals 3 again, right? Okay. Is that okay? Yeah, I can have 2 of the same answer. I actually told you what this is called. Does anybody remember?
The M word.
The M word, yeah. What is that M word? Multiplicity. Good. You were close. Multiplicity. Okay? Guys, bring it back. Seriously. We're not going to get through all this stuff today if you don't stop. So, 0, that's just one answer, correct? Which means the multiplicity at x equals 0 is just 1. Okay, I only have one answer of that. Then I have x equals 3, which is 2 answers. So my multiplicity would be 2, okay, at x equals 3. That is going to be important today. Okay, get to your 3.8 notes. Whoa, what is happening here? Get to the 3.8 notes, and let's get started. Let's get started.
Oh,
Ugh.
I do not want to work today.
Sorry. Story of my life. I don't want to come to work today. But guess what I did?
You can.
I came. Actually, I love my job. What am I saying right now? Okay. Equation. Y equals 3. Y equals 3. What's the degree of that? What's the highest exponent on the x?
3 and 1.
Is there an x in that?
No.
No, so it'd just be a degree of 0. Okay, there's no x in there, so technically that'd be x to the 0. Okay, we call this a constant. When we have just a number without a variable. Okay, if I were to graph the line y equals 3, what would that look like? What? A horizontal line. That's the word I'm looking for. Good. A straight horizontal line. Perfect. Put that word in there. Okay? Need to know that. Then we get into something that looks like y equals 3x plus 4. What's the highest degree on that? Highest exponent.
Oh,
1. Okay, it's got a degree of 1. We call this a line. It's linear. Okay, it's got a slope though. Okay, y equals 3 doesn't have a slope, but y equals 3x plus 4 does have a slope. What is the slope? 3. Yep, and the intercept would be 4. Y equals mx plus b. Perfect. Okay, next one. The degree is 2. Okay, the highest exponent is 2. That's what degree means. What does something with the highest exponent of 2 look like? Starts with a Q. Yeah, these are not quadratic formula, but just quadratic. Okay, and those make what kind of shape? Kind of like a U shape, similar to a U shape. Yeah, parabola is better. It's a better word. Okay, then we get into x to the third. We've not learned this yet. We've not learned this yet. We will learn this next semester. Okay, degree is 3. We call these cubics. That'll be fun. And then we get into degrees of 4, 5. They just keep getting bigger. I'm not even going to give you those words because you don't really need to know them. Okay, but these just keep on getting bigger. And we notice, just because we know what these first 3 look like, those look pretty different, don't they? The degree really matters as far as what the shape of this graph is going to look like. Okay? And just so we're clear on what degree means, because I know we're throwing around a lot of vocab. Woo, I can't talk today. A lot of vocab words. Degree just means your highest exponent on the x. So highest exponent. And we've actually talked about what the highest exponent tells me. It tells me something important. Yeah, how many factors, also how many solutions, right? Good. It's also going to tell me one more thing. One more thing here. Think about like the x-axis here. If we're talking solutions, can't we find those by looking at the x-axis most of the time, the real solutions?
Sure.
Yeah, okay, so my real solutions are found by looking at my x-axis. So this is going to tell me how many times I might, keyword is might here. Don't forget that word. How many times I might touch the x-axis. Okay, because 2 things are going to have an influence on that. And that's going to be that multiplicity that we talked about, and then also our imaginary solutions that we'll talk about in a little bit. What? Yeah, we'll get there. Okay. Today, I think you're really going to like the graphing today just because it's kind of just like rough sketches. Okay, these don't have to be 100% accurate. A lot of times our graphs are going to look a little bit different, and that's going to be okay. All right. But before we get into that, let's sketch some of the graphs that we do already know. Okay, so like for instance, y equals 3. You told me that was what type of line? Horizontal. It would be through 3 on the y-axis, right? So just a rough sketch. These don't have to be perfect. Okay? Go ahead and sketch what 3x plus 4 would look like. Y equals 3x plus 4. Put that on the next one. That's linear.
I don't know what this means.
What y equals 3x plus 4 means?
No.
Okay, just try.
Like, I don't know how to graph that.
You don't know how to graph that? Okay.
Oh, it's just like, isn't it just
It's
like,
y equals mx plus b. So think about that. Starting at 4, good. And what's the slope? 3 over 1. Up 3 over 1 or down 3, left 1. So it's going to look something like this. Just a rough sketch. Okay, then we have quadratics. Okay, again, we're just going to do a rough sketch. I'm just going to do the parent function just to keep this easy. Y equals x squared. That's going to go through have a vertex at the origin, right? Just kind of be like a U parabola shape. And then we have cubics. I'm also going to do the parent function of this. We've not seen these yet. They actually look a lot like our square and cube root functions, but instead of being horizontal, it's going to be more vertical. So they're going to look like this. Okay. So, as you can see, these look different, don't they? All of them look different. Okay? Then we're going to get into some bigger ones. Okay? Some things that look, the equations at least, look different. Okay? Here's what I want you to do. I want you to partner up. Okay? If you're in a group of 3, then two of you will work together. Okay? I need one of you to go and type in this first equation to Desmos.com. Okay? And then the other one is going to type in the second equation. So you're going to Desmos.com. You're clicking on that graphing calculator link, and you're typing these in. Okay, so if you graphed the first one, it looked pretty darn weird, didn't it? Yeah. Okay, I'm looking over at Grace's graph here, and it kind of like resembles like this shape. Yeah, kind of weird. Okay. What about the second one? What does it look like? It's a quadratic that goes upside down. Okay, perfect. Perfect. Okay. So the first one, as x goes to the left or to the right forever, what's y doing? It's going up to positive infinity. Okay, what about number 2, the second one?
Negative infinity.
Yeah, whether I go left or right on that thing, it's going to negative infinity. Okay. That's important. Okay, both of them are ending in the same direction. Why do you think one of them's going up and one of them's going down?
Positive.
Positive what?
The first coefficient.
The leading coefficient, okay? The leading coefficient, we've talked about that. If we make that value negative, it reflects over that x-axis, right? Okay, what I want you to do next, whichever equation you had, it doesn't matter which one. I want you to go change your highest degree to a 3. Go change it to a 3. And then compare these. Compare with your neighbor. What happens when the highest degree becomes a 3?
Mine did nothing.
Yours did nothing. It should have done something.
Cubic.
It becomes cubic? Okay, what does that mean as far as the shape this takes on? It does both sides are going different directions, right? The ends. So the left end is going one way and the right end's going another way? Yeah. Okay, we would call that opposites. Okay, compare with your neighbor. Okay, the left side of one of your graphs is going up and the left side of one of your graphs is going down. Reflects. Whoa. Okay, so we might have just discovered something really cool. Okay, based on the really cool or what? Or just too much work. I don't really think it was that much work. I think you guys kind of already knew it. Leading coefficient, but also the degree or that highest exponent, if you want to write that in the second blank. That's going to tell me what this thing is going to do. It's going to tell me what it looks like, what way it's headed. Okay, those two things. They are important. Okay. And we'll notice that there's actually a pattern here, okay, that we have pretty much already discovered, okay? You can write this in terms of just going up or down forever, or you could write it in terms of going positive infinity, negative infinity. I don't care, okay? I'm just going to do left, right, up, and down just for clarity's sake, okay? So if we have a positive leading coefficient and we have an even degree, the left side of this thing, is that going up or down? It's going up. And the right side is also going up. Okay, an example of this would be a quadratic, like the parent function, 1x squared. It's going to look like that, okay? Meaning that the arrows, the end behavior of these, both of them are going up. Okay? I want you to fill in the rest of this chart, okay? You can use Desmos. You can literally type in any positive leading coefficient and any odd degree and find that next box, okay? Anything is going to work as long as you do this correctly. So fill in the next 3 boxes and then we will talk about it here in a second. All right, so if we put in a positive leading coefficient and we put in an odd degree, okay, so again, back to this, positive leading coefficient, odd degree. Left and right, what's happening? What's the left side doing?
Odd degree, left is going up.
Down.
No, it's going down. Okay, if the positive leading coefficient, that means it's going down, and the right's going up. Okay, just like a positive sloped line, just like this, right? That would have an exponent that was odd, it'd just be x to the first. Okay, starts down, ends up. So if we want to draw in these arrows to our boxes, we can. Okay. Cool, and then we go back to even degrees, and we're doing a negative leading coefficient. Both are going down. Perfect. Just like a negative quadratic, right? Both would be going down. Down, down. Those arrows are ugly, I'm sorry. Okay, then odd and negative would be
Left is up, right is down.
left is up, right is down. Just like a negative sloping line, right? Left is up, right is down. Perfect, okay? And again, we call those end behaviors. End behaviors. We need to know those, okay? You've got to, I'm not going to tell you to memorize that table, but just think of ways that you can come back to this, okay? That those can make sense in your head because these are things you're expected to know. Okay, and then we get to our fun multiplicity rule. So, if the multiplicity is odd, meaning there's one answer that is this, there's three answers that are this same thing, or five, okay? This is going to be a line that crosses through the x-axis. If there is an even amount of one answer, okay, so two of the same answer, four of the same answer, and so on, this is going to be a bounce on the x-axis. Okay, the difference in what this looks like. The difference in what this looks like. If I were to go through the x-axis, I am literally crossing it. I'm going through. Okay? If I'm going to bounce it, I am literally going to hit that and go back that opposite direction. That is the difference between a through and a bounce. Through is odd, bounce is even. Multiplicity is what we're looking at. Questions there? Okay, because I knew you'd be brain dead by this point, which hopefully you're not. You guys seem like you're doing well. This was our warm-up question. So typically we'd factor that out and we'd find our answers, but we should already have those answers because we just did this. Tell me what my three answers were. 0, 3, and 3. Perfect. Okay, we factored it out. We found those answers. Love it. Okay, here's how this works. So the first thing I want to do is I want to find those end behaviors. You can go back to your chart if you need to, okay? If I've got a positive 1 as my leading coefficient and I've got a degree of 3, do we all see that? Yeah. Tell me, what are my arrows going to do on the left and the right?
Left is going down, right is going up.
I love it. Left is going down, right is going up. Positive leading coefficient and odd power. That tells me left is going down, right is going up. Okay? Then I have my actual answers. Okay, my solutions are at 0 and 3. So I'm going to put a point at x equals 0 and x equals 3. Okay? How many times does x equal 0? 1. So that means that my multiplicity is just 1. Is that going to be a through or a bounce? Is that an even or an odd number? 1. Odd, which tells me through. Okay? Then I see that I have 2 answers of 3. That tells me that my multiplicity is going to be 2, because there's 2 of those answers. Is that going to be a through or a bounce? A bounce. Okay, so now I'm just solving this as if it were a puzzle. I'm going from the left to the right. So I take that arrow on the left. Means I'm going to need a rise here. The first number I'm going to hit is 0, and it tells me to go through it. So I'm literally crossing, okay? And then it tells me to bounce on the 2. Sorry, the 3, not the 2. Bounce on the 3. And then we're ending up. So it should look something like that, okay? If yours doesn't look perfect like mine doesn't, that's okay.
Can I type them in the decimal?
You can. Yep, see if it's going to model something like that. It might look a little different, but it should take on that general shape. Yep. Okay, cool. Thanks for checking us. All right. Last really new thing that we're going to talk about, well, second to last new thing we're going to talk about is going to be these max and min points, which we actually have already talked about, so it shouldn't be that new. One thing that's important, though, when we're talking max and min, these have to be turning points, okay? So a lot of these graphs, guys, are you listening to me? A lot of these graphs are going to go maybe to positive infinity, maybe even to negative infinity. That's not a point, okay? Technically, that would be the highest and the lowest place that these things reach, but that's not a turning point, okay? A turning point is going to be what can be a max and what can be a min, okay? Maxes and mins are only going to be at turning points. What happens at a turning point? I change direction. I love it. Yep. I change direction. So if I'm not changing direction, it's not a turning point. It can't be a max or a min, okay? So if it is the highest point around, that's going to be a max or min? Max. If it's the lowest point around, a min. Okay, together we call these relative extrema. Okay, that's just another vocab word. Not overly important. Don't stress out about the vocab. Okay, you just need to know how to spot a max, how to spot a min. So, on this guy right here, I want you to circle all of the points where you turn direction. All the turning points. Where do you change direction here? How many times? 3. 1, 2, 3. Okay, which ones are the max, or which one is the max? The second one. You got it. That's the high point. Okay, is it the highest point this thing's going to reach? No, because it's going to infinity, but it's the highest turning point. That's why it's a max. Okay, what about the min? Okay, so technically I would agree with you. This is my lowest point, so I would call that the minimum. But when we talk relative minimums, it actually means any low point that's a turning point. Okay, so really this could also be a relative minimum. If you only put the lowest one, I'm probably not going to count it wrong. But just know that technically a lot of textbooks like to throw in both of those because they're both low points that are turning points. Are we clear? Sure? Okay. Skip this page. I'm not doing that. Okay. I'm going to do this first one for you, and then I'm going to turn you loose, okay? So here is how we sketch these graphs. This is on your test, which is your final, again, so this is important. So please be paying attention right now, okay? The first two letters, A and B, okay, those are important. These are the most screwed up ones, the ones that people tend to screw up the most, okay? Even degree, positive leading coefficient. I just need to put my arrows where they go. If it's an even degree and a positive leading coefficient, where are my left and right arrows? Up. You got it. Pay attention to that because those are going to be different for every single one of them. Make sure you get those right. Okay. Then it's telling me real root at -1, 0, and 5. That's where my points go. -1, 0, and 5. And it tells me what the multiplicity is, which I need to know, okay? So if the multiplicity at -1 is 2, is that a bounce or a through? A bounce. The other two, it's just 1, which means a through. Okay, and then the last new thing that we've not talked about, okay? Imaginary solutions. Sometimes these show up. They don't always show up, but sometimes they do, okay? And these are just going to be bounces that happen above or below the x-axis. These cannot happen on the x-axis, okay? If they did, they would be real solutions, okay? They would be real solutions if they happened on the x-axis. These have to happen above or below, okay? So, for instance, it tells me that there's 2. We know imaginary solutions always come in pairs of 2, so that's not a shock to me, okay? It does not matter where I put them as long as I don't put them on the x-axis. So one thing I like to do is I like to just kind of get them out of the way. Just put a little like double bump there. And see how that bumps on the left and the right. I don't really care exactly what it looks like because yours might look a little different, but just know that it's two bounces that need to occur somewhere not on my x-axis. So I just got them out of the way. I'm done with them. Okay? And now I can just go on to the rest of this. So it says bounce at -1. That's the first number I'm approaching. So I'm going to go -1, bounce it. And then the next two numbers I need to go through the x-axis. So after I bounce at that -1, I'm going through 0, coming back around, going through 5, and I'm going back up because that's where I need to end. Okay, these look weird. I get it. These look so weird. They are weird. It doesn't look fun. I kind of think they're fun. I don't think they're bad because they don't have to be perfect. They're just kind of like a puzzle, okay? All right, the next two on this page are yours. Ready, set, go. All right, I'm hearing a lot of chatter. Let's get going on this. Okay, number 2 says odd degree, negative leading. Left and right arrows. What we got? Left is up, right is down. I like it, okay? Just like a negative sloping line, okay? That would be an odd degree and a negative leading coefficient. If I had a negative mx plus b, it'd be a negative sloped line. Good. 2 imaginary solutions. Where do those go? At the beginning or the end, probably. That'd be a good place for them. It doesn't matter where, okay? Just make sure you put them somewhere. That looked kind of weird. I'm going to do it a little better. There we go. I'm going to do that. Okay. If you put them at the beginning, though, you're right. Okay. Then we have our real roots at, where are these points? 0 and 5. And is 0 a bounce or a through? A bounce. And is 5 a bounce or a through? A through. Why is it a through? Because it's odd, okay? 2 is even. Good deal, okay? So from the left to the right, I need to bounce that 0. Whoa, that looked weird. I'll try that again. Bounce the 0 and go through the 5. Should look something like that. How many of us did well on that? Good, good. Those are the imaginary solutions. You could have put them on top too. Those are just bumps that are not on the X. Any other questions? Boys, how'd you do? Do well? Okay, cool. And then we got number 3, odd degree positive leading. Left and right arrows. Down and up. Good. Down and up. Those are my end behaviors. Do I have any imaginary to deal with? Not here, which is good. I don't like those. Those are dumb. Okay? Where are my roots going to be?
Oh my god, what?
Oh my gosh, what?
You
didn't do this one?
I did the bounces at the beginning.
You did the bounces at the beginning. Yep, don't do imaginary if it doesn't tell you that there are any. Okay, at -4, is that a bounce or a through? Through. At -2.
Through.
At 0.
Through.
At 2.
Bounce.
Bounce. Perfect. So it should have looked something like this. Through, 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 bounce. Okay, so a couple people are confused, okay? Remember that when we go through, okay, when we go through, or even when we bounce, we have to create those turning points, okay? So somebody during 5th hour yesterday, here's what they did, okay? And they could not realize why they were wrong. And I'll tell you why they were wrong, because they did this.
That's what I did.
That's what you did. Okay. This is not correct. And here's the reason, guys. Listen to me. Please stop talking. You are not going through the x-axis. You are just staying on it. Okay? You've got to actually physically cross it. Okay? You've got to cross it. You've got to create a turning point. Right there, that's just a straight line. And if you go type this thing into Desmos, actually there's no equation, but if there was one, you would not find something that looked like that. There's not going to be anything that looks like that. Could be 3 lines put together. That could be a piecewise function. Absolutely. Okay. But that is never going to be a polynomial function. Okay. It's got to create those turning points. So definitely don't do that. Okay. Make sure that if we are going through, we actually go through. Are we clear? You guess so? Any questions there? It's very easy. I like that.
I figured it out. We're good.
You figured it out? Any other questions? Are you guys clear in the back? Okay. Bailey, are you good? You're good. Okay. Last 2 questions, guys. Last 2 questions. I want you to try your best on these. Pretend this was an EOC or an ACT question. Okay? Use process of elimination if you need to. Try. Okay. Is the degree 3 or 4? Tell me your thought process behind this. Why has it got to be 4? Yeah, they're both ending in the same direction. Good. How many real roots? How many answers do they have to be on this? If the degree is 4? 4. Do you see any imaginary bumps? No. So there's 4. Okay. Then it says to name each root and state the multiplicity. Okay, I can see where you might have put 3 because one of these roots has a multiplicity of 2. Okay, but technically it's still 4 answers. So let's see where these roots are. The first one is at x equals -2, and the multiplicity of that is just 1 because it goes through. The next one, 0, and the multiplicity is also 1. Okay, and the last one, 1, and the multiplicity is 2, which means 2 answers at x equals 1.
Well, how do you only have 3 numbers together? You have 4 real roots.
Because the multiplicity is 2 at x equals 1. So it's 2 answers. It's 2 roots that are the same thing. Okay? How many imaginary then? We know real plus imaginary has to equal the degree. So how many would that mean? None. 0. Okay, or we could just put none. And then circle any points that might be maxes or mins. So those are just any low or high turning points. Bottom is a min.
Top,
This guy?
max,
Yep.
and then bottom is a min.
Good. That's it. That was very, very similar to the example that we already did. Okay, next one. Is the degree 3 or 4?
3.
Gotta be 3. How many real roots?
3.
Okay, here's where I would accept either answer because we kind of are lacking information on this, okay? You could have said, if you said 3 real roots, okay, and you could have just put it at x equals, I don't even know what number that is, I'm going to guess -1.5, with a multiplicity of 3, which would then mean that you had 0 imaginary, and we don't have any maxes or mins because we don't change direction on this. So there shouldn't have been any maxes or mins regardless, okay? That's option 1. The other option that you could have done is you could have said, hey, I think there's only 1 real root because I go through this line and I'm going to call that a 1, which then would mean I had to have how many imaginary? 2, okay? And if you thought maybe that this little bump here, bump, that was imaginary, I would probably call you right there too, okay? I'd probably count either of those right on the test just because we are lacking information. Okay, so in this case, you would have had a multiplicity of 1 on x equals -1.5. Okay, either answer you gave me, I don't care. But if you did not give me one of those 2, then you are wrong. Any questions there? Are we good? Are we good? Okay, that's it.